And it's just the things in the title. Today we'll talk about rates of change of a function, even and odd functions, intervals of increase and decrease of a function. I might flip up sometimes and say the word intervals of monotonicity, where monotonicity is just a fancy word that means either increasing or decreasing. Its behavior is the same. It has one behavior, thus the monotonic. I'll try to avoid using that fancy word because it just means either increasing or decreasing. And extrema, which is just a fancy word for either maximums or minimums. So let's start in on this. Topic 1, rates of change. So we talked about the notion of slope for a function that's linear. The slope is just rise over line. It's the same no matter what points you check, as long as you have a straight line. If you have any other nonlinear function, like say this one, you can still talk about rates of change. You just need to think about what interval of inputs you're thinking of. The average slope of the graph of y equals f of x, also known as the average rate of change of f of x, over an interval x1, x2, is the slope of the straight line from x1 f of x1 to x2 f of x2. So, that blue line, the slope of that, is the average slope of f of x equals x squared plus 1 over the interval -1 to 2, because it's over the interval -1 to 2. You okay? Yeah. Maybe I'll even do a little of this. Is it still big enough to read? So now everything's actually on screen. Alright, so the average rate of change is just the slope of the straight line between those two points. Sometimes that's also called the secant line. Let's write down some formulas. So it's the slope of the straight line between these 2 points, x1 f of x1 and x2 f of x2. So that means the average slope, also known as the average rate of change, is, well, it's a slope, so it should be like a change in y over change in x kind of thing. These y's are function values, and the function's called f. These should be things that look like the change in a function divided by change in x. And I haven't written down a formula yet. I've just written down different symbols you might use to describe it. But you also can write down the formula. It's the change in the y value. So f of x1 minus f of x2 all over x1 minus x2. That feel pretty okay? Hopefully it feels like pretty familiar if you're just thinking about the definitions. Let's check our understanding by just making an observation. Let's compute the average slope of this function over that interval, and maybe I'll propose 2 ways. You can do it via the graph, and you can do it via the formula. And let's think about it in terms of the graph loss. The slope of the average rate of change of this function, the average slope, is the slope of the straight line between those 2 points. What's the slope of that straight line? Yeah. That agree? Nice. The average slope is, I'll get some space, it's 1, and it's 1 because I guess the total change in y is 3. The total change in x is 3. That's 1. Feel pretty okay? Let's also use the formula. we have a formula for this function. This function is given by f of x equals x squared plus 1. So using that formula, that means you can compute the average rate of change by plugging these points into the function and then dividing by the change in y. So that will be, some color coding I think will help. Plug in x equals 2 to this formula. 2 squared plus 1. So that's from this point. Plug in this number to that formula. Minus negative 1 squared plus 1. Close parentheses. All over 2 minus 1. People happy with where those things came from? So I plugged in x equals negative 2 in the green head to this formula. I plugged in x equals negative 1 to the same formula. Then I divided by 2 minus 1. That looks like something you can do. Let's go through and do it. Certain this. 2 squared is 4. Plus 1 is 5. Equals 5. Minus negative 1 squared is plus 1 is 2 minus negative 1 is 3. Wait. Double negative becomes positive. Oh, is 5 minus 2 all over 3 equal to 1? Cool. How do people feel about that? So if you want to compute the average rate of change, if you have a picture of the graph, then draw a straight line between the two x values. And do that thing. If you have a formula, you can do that using this formula. Do you all think you can do it for this next example? Compute for me the average rate of change of this income over the income negative 2 plus 1. And well, maybe I'll ask this. Is anyone unsure on how to proceed? Excellent. Then I will be quiet. You'll get a result. You'll talk with those around you about what you did. Possibly compare your answers. Cool. People are you sure? What do you get? Yeah. A slope of 0. Anyone else get a slope of 0? Any different answers? What do you get? I got negative 1. Any other answers? Negative 1. Negative 1 seems more popular. Let's try to compute this a few ways and see what we got. So when you computed the slope, what strategy did you follow? The graph or the formula? Okay, follow the graph. I also have one for formula. We'll do both. Let's do the graphical one. Excellent. Do you agree about negative 1 now?
Yes.
Excellent. I'll still try. So if you want the average rate of change from negative 2, x equals negative 2, to x equals 1, let's find these points. That sure looks like negative 3, comma, 1, not negative 2, comma, 1, 2, 3, 4, 5. 1, 2, 1, 2, 3. Chris, come on. Just because it's blue doesn't mean that's where you go. 1, comma, 2. Do you want the straight line between those 2 points? What does that slope appear to be? Sure looks like negative 1. Whenever you do something just in terms of the graph, right, you're only as precise as the graph is. It sure looks like it's negative 1. It could be off by some small number. Let's also do it using the formula. Average slope is. Alright, so the game is going to be, and maybe just for emphasis, do you think it matters which goes first, the negative 2 or the 1 when I do the computation? As long as you're consistent in the top and bottom, we'll get the same. And maybe just in order to check that, those of you who did the computation for your formula, you plug in negative 2 plus or 1 plus? 1? Cool. And I'll just plug in negative 2 plus, and you'll see how you can actually do it. And more importantly, that data. So, let's plug in negative, did you say negative 2? You said 1 plus. Okay. Then I will plug in negative 2 plus. So plugging in negative 2, we'll get negative 2 squared plus 1 minus 1 squared plus 1 all over negative 2 minus 1. And let's do the computation and see what happens. I guess the denominator plus 1. Negative 2 minus 1. Negative 3. Negative 2 squared. 4. The negative sign doesn't matter. So 4 plus 1 is 1 squared plus 1. 5 minus 2 over negative 3. Is that negative 1? So those of you who did it on your own, you probably got something off like this where you go like 2 minus 5 over positive. That's exactly what happens in the negative change point where you switch to our points. The numerator and the denominator are negative. Negative divided by negative and negative. Yeah. I'm feeling good? Alright. Here's the notion of average rate of change, also known as average slope. And there's, so here's one takeaway that I want to point out. Where do you check the average rate of change basically? The average rate of change when you compute it on the same function, 2 different sets of points. You have an answer of negative 1 and an answer of 1. Do you think we can get lots of other answers by taking different points? Yeah. Is there demand to do some more examples? Folks, say yes? Alright, cool. We're happy with average rate of change. Let's move on to the second topic, which is even and odd functions. So these will be certain symmetry conditions that functions sometimes satisfy. And this is one of the topics which people come into this stuff already having various levels of already work stuff. How many people have thought at all on even functions in the past? How many people have an idea of what even function means? Cool. And so if I say what's the definition of an even function? Okay. It's like that. It's more precise than this guy. So what you said was both ends of the function do the same thing. But it's more than just the ends. It's everything in between. If you go left and you go right, you get the same thing. Yeah. You replace x with with negative x, you get the exact same function. Yeah, that's one of the things that I want to write down. A function is even if f of x is the same as f of negative x. You know, if you input with negative that input, you get the exact same thing out. And so that's often used, they should have the same end behavior or, you know, whatever. But like, more than that even. You get the exact same behavior on the left and right of the y-axis. So in terms of a graph, a function is even. A function is even if its graph is preserved by reflection over the y-axis. And let's see if this agrees with intuition. So here's a function, f of x equals x squared minus 1. Let's see what happens when you reflect over the y-axis. So here's the y-axis. Here's the point on the graph of the function that's reflected over that pink line. So there it gets to the pink line. Now it has to travel the same distance the other direction. Does that give the point still on the pink, still on the graph? Yeah. And let's just check some more. You keep on reflecting points. Does it look like this graph is resolved by reflection over the y-axis? I would then call this an even function. If I say a function is called odd, how many people have formed an odd function before? With the recollection of what even means, what does it mean to be odd? Yeah, share that. Symmetrical with origin. Awesome. Okay, and doesn't reflect symmetrically. I'll write down the plus thing and then we'll talk about that, because there's like a weird subtlety. So a function is called odd in terms of a graph if its graph is preserved by reflection over the origin. And so the other thing said was, if its graph is not resolved by reflection over the y-axis. So that's what it would mean to not be even. But unlike an integer, is definitely either even or odd. A function can be neither even nor odd. So not being even is not being a function is odd. Also, there is a single function that is both even and odd. So you should think of this in terms of like evenness of natural numbers. I'm not just thinking about like polynomials and everything. Right, so the graph was resolved by reflection over the origin. Let's think about what that does. So if you take that point in the xy plane, well, that looks like two mediation. You reflect that over the origin, right? You land. Very confusing. Yeah, but say lava. I think it's the right thing to count. Negative 2. The x value becomes negative and the y value becomes negative. So an odd function is a function which has the property that when you make the input negative, the output becomes negative. So a function is called odd if f of negative x is the same as negative f of x. I'll write it in a different way, which hopefully is pretty obviously the same. Or negative f of negative x equals f. Alright, so you can take that equation and multiply both sides by -1, you get this equation. Different ones will be useful in different times. Alright, so let's check these things for whether they're even or odd. Let's start with this one. If you take this graph and reflect it over the origin, do you get the exact same graph back? Let's check and see. So I'll draw a point on this graph in blue. I'll reflect it over the origin and land down there. Is this new point on the original graph? Nope. So this is not an odd function. Let's check this one. In fact, maybe I'll just ask you. So take that thing, reflect over the y-axis. Is that graph even? So yes. So far it is not even. Cool, not an answer. It is not even, and let's check why. I'll take this point on the graph. I'm using this color to check for evenness. Take this point. I'll reflect it over the y-axis. Is that new point on the graph? Nope. So it is not even. Is it odd? So for yes, it is odd. So for no, it is not odd. Cool. And on that one, it is in fact odd. But not that answer. So let's go through and do a quick check. Maybe I'll do it two different ways. So I'm using blue for this check. Let's pick a point on this graph, and let's reflect it over the origin. That means go through the origin and then go the same distance but the other way. Is this new point that you land up with still on the graph of the function? Yep. And does that appear to happen no matter which point on the graph you took? So it is odd. And here's another way to check. So, your graph in front of you, keep looking at it. You can reflect over the origin by also pinning down the origin and rotating 180 degrees. So I will do exactly that. I will pin down the origin. I'll rotate my tape for 180 degrees. Does that graph still look the exact same as the graph you have? That means it's odd. Nice. And this last one. So take a look at the graph of this function. Looking at that graph, does it appear to be even? Yes or no? I'll hold on for a second, maybe discuss with those around you until you feel confident. So yes, it does seem to be even. Anyone but no, it does not seem to be even. So far, it is not clear. Alright, well not all the hands went up. Okay, let's talk to it. Let's do this, and I'll let that like you telling me why.
I was just saying you can see the experiences like not enough words also. Like if we reflect across the y-axis, then also axis, but it wouldn't reflect across the
yeah, so it's not even, and also according to what you just said, is it odd? No, so it's not only even more odd. It's not even because when you reflect over the origin, you change the graph. When you reflect over the axis, you change the graph. And when you reflect over the origin, I think this is a good one to check, you wind up with something that's still not on the graph. Let's do okay. So, as I said, there are functions that are even and not odd. There are functions that are odd and not even. There are functions that are not even or odd. There is exactly one function which is both even and odd. There's exactly one of them, and I'm not going to tell you what it is. I can tell you what it is at some point. If you find yourself when you think about that question, think about that question. Maybe you get more time class today, don't tell me what it was, but then maybe you can tell me what it was. What is that function? There's exactly one of them. So, we talked about evenness and oddness via graphs. Let's also check via formulas. So remember, a function is even if f of x is the exact same as f of negative x. A function is odd if negative f of negative x is equal to f of x. So let's try to use those to check whether these functions will be even or odd. And maybe we'll only check one thing. So this was a function that on the previous page you told me was even. Let's check whether or not it's even by doing a computation. Let's compute f of negative x. And doing that is just going to be an exercise in carefully doing your function composition. So let's compose this function. So that means I need to take the formula from f of x, which is something squared minus 1, and plug negative x in for that something. Alright, so let's make that simplified. What simplification do you see for that being written down? Yeah, let's think about that squared. What happens when you square a negative? It becomes positive. The negative sign doesn't stop. Negative times negative becomes positive. So this is the same as just x squared minus 1. Is that the same as the formula for f of x? So this sucker is even. The second function was one of the three functions on the previous page. So let's take a look at the previous page and look at the graphs. Is that function, according to the graph, even or odd or not odd? So let's check whether it's odd by doing this. We can also check whether it's even if there's demand to, but let's do the one that we'll get in a minute about. So that means I'll need some color coding. Let's make that blue, and this will be the bit that is in red. So this will be negative. Then the formula for g of x is something cubed minus something. And the thing you should plug into these somethings is negative x. And then we just need to start to really simplify. So if we were to encounter that expression in the lab, what simplification would you want to do? Yeah. The double negative will become a plus. Okay, cool. So, leave this negative alone. There's one other thing I want to do in this one step. Equals. Negative. Parentheses. Double negative will become a plus x. Let's also look at that negative x cubed. What's negative x cubed? I meant so. Yeah. So you can pull the negative out of an x cubed. Negative x cubed is negative x times negative x times negative x. Those two negatives cancel, leaving you with x times x times x, or x cubed, and it's negative. So negative x cubed plus x. Alright, what simplification seems sensible to do next? Distribute the negative from the outside to the inside. I know, like, any of these tests could have been done in any law, so we're doing things slightly differently. That's cool. Distribute this negative through. Negative of a negative is positive. X cubed. Negative of a positive is negative. Minus x. Is that the same as the formula for g of x? This thing is odd. Nice. Alright. H of x equals x cubed minus 1. I guess if you want to, then look at the graphs on the previous page to get an idea. Like, you just saw that formula, what would you think? What's a gut reaction? Even or odd or not or even? Odd? let's go through all check 1 and Jill check the other. Should I use the check called Cuban or a check called R? Should I check called Cuban? Should I check called R? Cool. I will do the check called oddness. If anyone wants to do the check called unit, feel pretty confident in my ability to see me do the check, do it, and we'll see what you have to say. So, let's think about negative h of negative x. I'll do the same bit of color coding because I find it useful for me. So maybe you ask, how many people have picked themselves up a set of colored pens by doing that? Yeah. If you like, the brand that I've been using is, I think the Colors brand. It was a cheap brand I found on Amazon. If you want a good brand, you look for friction spelled with an X. In general, the impression I get is if you can find a brand of any sort of stencilery that has Japanese lettering on it, it's good. This doesn't, and it's not so good. But it's passable. Anyway, tangent done. Negative h of negative x. So, this negative will come along for the ride. Next, I want the formula for h of x is stuff cubed minus 1, where the stuff is negative x. And let's use some basis. Negative x is negative cubed on that top. Yeah, it's really hard to don't pronounce parentheses because otherwise we're saying negative x cubed is equal to negative x cubed. You can't tell where the negative sign goes. Yeah, negative x cubed becomes negative x cubed. Haven't dealt with this negative sign yet. We will in a moment. And I guess the negative 1 is still just a negative 1. You need an equal sign between things that are supposed to be equal. Alright. Last. Distribute the negative. Which I guess you can do standing by doing that. But then I'll write it out, x cubed plus 1. Is that the exact same formula that you had for h of x? Nope. In fact, it's different in a very specific way. There's a negative 1 instead of a plus 1. So this sucker is not odd. So this is you plug in just h of negative x, what did you get? Yeah.
I got x for negative x cubed.
Which again is not the same thing as negative x cubed. Nope. Which is not the same as x cubed minus 1 because of that negative sign. Cool. Folks feel pretty good about the ideas of even and odd functions? Any questions about those ones? Alright. Let's think about intervals of increase and decrease. I'll color code blue for increase, red for decrease. So the first thing I'm going to try to convince you is that you definitely know what these terms are. By asking you, if I look over this x value, so I look right there on that function, does that function appear to be increasing or decreasing at that point? Increasing. So y values are going up when the x values go up. So it sure looks like at this point, this function is increasing. Which I'll show you in blue. Blue is actually all increasing. Yeah, you can see that actually. Now let's just figure out how far to the left or right you can go and still have it be increasing. How far to the left could I go and still call that function increasing? From negative 2. Well, I guess back to negative 2. Over this whole interval, the function seems to be increasing. How far to the right could I go and still have the function be increasing? almost to -1. So maybe in order to indicate that, about negative, let's say 1.1. So it looks like when that whole interval, the function is increasing. At that point, -1.1, it stops increasing and starts decreasing, I think. Alright, so right here it starts decreasing. How far to the right can I keep on moving before the function stops decreasing? Yeah. Right about x equals 1. And maybe just for consistency, looking at that formula for the function, would you call this function even or odd or neither? Odd. So I think there should be a symmetry. Those 2 points should be like the exact same points but negatives of each other. So I use the exact same x value as before but negative. So it's decreasing from -1.1 up to 1.1. And I'll put squiggly lines there to indicate that these are approximate values. And then I guess starting at 1.1 it starts increasing again. Approximately 1.1. And how long does it keep increasing? How long until it stops increasing? Right up until x equals 2. After a true function doesn't even exist, so it doesn't exist for us. Alright, so there's the notion of increase and decrease. People feel pretty comfortable? I'll write down a formal definition and we'll see if you find that it seems correct. What does it mean for a function to be increasing? Well, it should mean when you take an x value that's less than another x value, the y value should satisfy the same inequality. Blue, because blue is increasing. For all inputs, x1 and x2 in that interval, this I is an interval. If x1 is less than x2, then the resulting y value satisfy the same inequality. F of x1 is less than f of x2. And let's just see if that appears to hold water. So here are two x values, x1 less than x2, in the interval over which we say that it is increasing. There is f of x1, there is f of x2. Does it appear as though f of x1 is less than f of x2? That's what increasing means. When you increase the inputs, you increase the outputs. How would that change if I wanted to talk about decreasing? Well, let's maybe let's just try something. So there's an input x1, there's another input x2, there's the resulting output f of x1, there's the resulting output f of x2, which is greater than f of x1 greater than f of x2 or opposite. F of x1 greater than f of x2? Yeah, right, f of x2 is negative. F of x1 is positive. So I'm going to use like the ditto marks for all inputs x1 and x2 in the interval I. If x1 is less than x2, then f of x1 is greater than f of x2. And maybe I'll put this in there also, this joke says that. So a decreasing function flips inequalities. If you have two inputs in some order, the outputs will be in exactly the opposite order. That's what it means to be decreasing. Hopefully good? Nice. 20 points. So if you want to look at this graph, tell me, where does that function fall on? At what inputs? Absolutely. Those are the places where it goes from increasing to decreasing. And I'll be approximate because these are approximate. There are the turning points. A turning point in our function is an input where the function changes from increasing to decreasing, or opposite, from decreasing to increasing. Let's feel okay? And we have these formal definitions, but you already know the ideas of what these things should mean. You know what increasing means, you know what decreasing means. A turning point is the place where it changes from one to the other. So, there's the notion of increase and decrease. You know how to work with that in terms of a graph. With my about 10 minutes left, let's switch topics again and think about the last thing in the list of 4 topics we want to talk about according to the title of today's lecture. And that is extrema. And maybe I'll start with just saying this. Extrema is the plural of extremum. Extremum is either maximum or minimum. And in general, whatever, that's good. So there's extrema is just plural of extremum. Extremum is just talking about maximum or minimum in the same law. Mathematically, you find them the exact same way either way. Let's talk about them. So, here's the graph of a function. And let's just convince ourselves that we know what these ones all mean. What is the maximum value that this function takes? Alright, so you just gave me like everything. -5, 5. And this is related to the maximum. So you told me everything, but I only want one of those to know. So for -5 and 5, which of those is the maximum value? 5. When I ask for the maximum value, I just want the value. The maximum value this function takes? 5. But you also told me the input that produces it. What input produces that value of 5? Yeah. So when someone asks you for a value, an output value, they want the y value. If someone asks for the input, they want the x value. Same question, but minimum. What is the minimum value this function takes? Say again? 2 -4. Awesome. So, let's now parse that into answering the exact questions as asked. What is the minimum value that this function takes? -4. And what input produces that minimum value? 2. So, here's what it means to globally maximize or globally minimize. There's one other notion of mathematicians think about an awful lot, and that's the idea of a local extrema. So whenever a mathematician says they want to estimate globally anything, they're saying if you zoom in really, really close to this point, you only see stuff really, really close to this point, does it look like it's one of those things? So let's see this in practice. The old document cameras were like way less stable, but they had one really good bit of shit where I could zoom in like 20 or 40 times and do this well. So what I put up with this. So let's suppose you only saw that much of the graph. If you only saw that much of the graph, would you say that that point looks like a global maximum? Nope. So that means that this point is not a local max. Because you zoom in really, really close, it doesn't look like an X.
Is there a point where if you did zoom in really, really close to that point, you would see something that looked like global max? Yeah. What X value are you thinking of?
0. If you zoom in really, really close to that point, does X equals 0 look like it produces a maximum? Yeah. This is what's called a local max. So what values for X locally maximize the function? Well, it looks like X equals 0 does.
Are there any other places that look like they are local maximum zones? How many people would want to say X equals -5? Here's an argument for it. Here's why I would. In order to be locally something, you have to be able to actually talk about all of the values here. And you can't even talk about an input of -5.00001. It's not even there. So you can't actually look close to -5.
Are there any inputs that seem to locally minimize? Yeah. X equals -3 and X equals 2. Cool. I agree. If you zoomed in really, really close to those 2 points, you would see things that look like global mins. So notice, it's possible for the global minimizer to also be a local minimizer, but it doesn't have to happen. When it happens at an endpoint, then it's not a local anything. So, let's just, with my remaining time, write down some formal definitions. An input C is a global maximizer for a function if f of C is greater or equal to f of x for all x in the domain of f. That seems sensible? An input C is a global maximizer if the output resulting from C is bigger than or equal to every other output. It has to be bigger than or equal to, otherwise you would be demanding that f of C is bigger than f of C, which isn't what you want. An input C is a global minimizer if, well, how would it change to make it a minimum? Yeah, the inequality would flip. F of C is less than or equal to f of x for all x in the domain. An input C is called a local maximizer if f of C bigger than or equal to f of x for all x near C. And near is an ambiguous word in this context. To make it precise, you would really need some language that's developed in calculus. And here by near, I mean as near as you could possibly get. And same thing for minimizing. F of C is less than or equal to f of x for all x near C. And because I have time, let's look back. X cubed minus 4x is the same as the function graphed on the previous page. Let's look at this function. What would you say the maximum value of that function is? Be approximate if you have to. Yeah, so the input that produces the max is about -1.1-ish. I guess you told me more than this, so I guess you probably looked at the machine. And let's just notice something. That value, -1.1, is a floating point. Extreme values tend to occur at floating points, or at the endpoints of the There's the last point on this. Is this person still on that one? Oh, that's a fair question. I think that I'm happy to where I am. Folks have anything they'd like to ask me on their way out? Ooh, did anyone already look at the homework that's assigned for today? Does that homework seem totally reasonable now that you've seen my thoughts? Awesome. Someone pointed out to me during the previous section that it was actually really nice where I had all the dates screwed up and I kept on looking at the homework. But all of was a sign, but what was really a sign? If I have an idea what the lecture was about. So it's one thing for you reading ahead in the homework. The class will go way out for you. Yeah. You have to be able to look on both sides of it. Okay. And there's nothing to the left of that.